Okay. Good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I left off last day, where I proved the first part of Kleine's theorem. That was where I could give you any regular expression, and I showed you a way you can construct an epsilon-NFA out of it. So we're going to do an example like that, and then we're going to prove the other part of Kleine's theorem, which is where I could give you any DFA, and I could turn it into a regular expression. So we should have time, hopefully, to do an example after that proof, showing you the other construction. So we're going to do this example first, and I really just want to hammer in the idea that, like, I really like this because it's because once you get all the cases, it's really just a matter of, okay, does it look like this? And then you draw out the epsilon-NFA, and then you start connecting them together, and they'll just start growing as if you're looking at the sub-expressions of the regular expression, just like in the proof. So let's consider this regular expression, 1 union 0. I'm going to put a star around all of that. I'm going to concatenate it with 0, and then I'm going to concatenate that with parentheses, 1 union 0, or 1 plus 0. So what I'm going to do is I'm going to try to build this construction by taking bits and pieces of this, and then I'm going to concatenate them all together, because you'll notice that I kind of have like 3 pieces here. I've got this 1 plus 0 with the star, and then I have this 0 here, and then I have this 1 and 0 here in parentheses. So it's kind of like 3 pieces. So I'm going to show you how we're going to start off with the 1 and a 0, because I'm going to use it to do the part where I have the star. So let's first consider 1 union 0. So we apply the union construction. So I'm going to apply the union construction. So that says union construction. I know, it's Friday, isn't it? So what does that look like? If I go to my proof, if you go back to your proof there, I showed you a picture where I had 2 immediate sub-expressions, and I had told you they're called R and S. So when I give you 1 or 0 like this, this is R, that's S. And we know the basis part of our definition of the construction, and that is simply going to be that this is the start state, this is the final state, and I label it with the symbol 1, and I can label this with the 0 respectively. Now, if these were just 1 and 0 on their own, that would be fine, but I'm going to take and apply the union construction. So what I do is I'm going to put epsilon transitions from what it's going to end up being the new start state. I'm going to use quotation marks around that because it's not really like, I'm going to leave until the end to label the start and final state, because I'm going to still add more things to this. So I'm not quite done yet. So for now, I'm just going to hold off on that. And the union, all I do is I take what would be the epsilon-NFA for R and the epsilon-NFA of S. Then I introduce the new start and new final state, and I put epsilon moves off of them. So notice I've just built out of 2 simpler expressions a new one. Now I have a new automaton I can work with, but I'm not going to label it quite yet because I'm going to be building up the things. So this is what 1 or 0 looks like. Now you might ask, Dan, okay, so I'm going to next apply the star construction. Next, I'm going to apply the star construction for the expression 1 or 0. So I'm going to apply star to this. So if you may recall, so what I'm going to do is I'm going to take this and I'm going to employ the star construction on it. So remember, you got to look at this like it's R, like this is the entirety, that's R. So I'm going to redraw that. So I have epsilon, epsilon, 1, 0, epsilon, epsilon like this. That epsilon's looking a little sad there. Okay, so now I need to put the start state. So I have a new start state. It's going to have an epsilon move. I'm going to have a new final state with an epsilon move like this. Don't forget that you take the old the old final state. You're going to draw an arc from that to the original start state on an epsilon move like this. And then you're going to employ another epsilon move from the new start state to the new final state. So this is what 1, 0 star would look like. So so far I have a couple pieces here. Notice that that's the piece I need for this. This is the piece for this. And now all I have to do is the piece for the concatenation. So let's do that. So let me move on over here. First, are we okay with this so far? So all I'm doing is I'm applying the cases from the proof that I gave last class. So just think union, concatenation, star. All I'm doing is I look at the operator and I say, hey, look, what construction do I use? Do I use the one that kind of puts them together like this, the one that puts them side by side, or do I put the one with the star where it kind of goes back and feeds into itself? So what I'm going to do is I'm going to continue it over here. So instead of doing concatenation separately, like as in like, oh, it's just 0, I could do that, but that's not terribly interesting. So I want to actually apply the concatenation, because obviously if I just wanted to have like 0, that's just simply, whoops, I need a 0 right, sorry, the expression 0 would be this, right? So I'm just going to do the concatenation. So let's do the concatenation. I'm going to do concatenation of 0 with 0, sorry, 1 and 1 or 0. so let's do this. Okay. So now, that's a very sad now. There we go. That looks better. Now, to apply the concatenation construction, instead of say 2, let's go with we. Now we, because we're doing this together, we apply the concatenation construction. 4, 0, 0, sorry, 1. We had the 1 right here. Although it doesn't make any difference, but I'll put the 1 right there. 1, 0 like this. So all I'm going to do is, so remember, I have 0. So for the concatenation, I start off with my start state from the original for R. So remember, this is R right here. This is S. So this is the start state for the new automaton. Then I have an epsilon move that's going to get me from the final state of the original for R to S. But what's this? I already drew it over there. That was the first one I drew. So I'm just drawing out the same one we had before. 0 with the epsilon moves like this. And I think I got everything there. So this would be the new start state. This is the new final state. So you might ask, Dan, okay, so like, what do you got to do next? So now I got to put everything together. I need to concatenate 1 union 0 star with this. So now for the sake of board space, and for the sake of your paper in front of you, or if you're taking notes at all, I'm going to be somewhat lazy with this, but I did draw the entire picture in the notes, if you're wondering. So what I'm going to do is, I'll say finally, we put the whole automaton together, resulting in the following. This is following epsilon-NFA. So what do I need to do? Well, remember, all I have, so let me just do this for dramatic purposes. So you may recall that over here I had 1, 0 star, right? So I had 1, 0 star. So let's see. Can you guys see the final state of 1, 0 star by any odd chance? If not, I can move it a little bit more. Okay. There we go. There we go. I think we can see the final state. Can we see the final state? This guy right here where my finger is? Yep. Okay, good. So now that's 1, 0 star. So to do the concatenation, what I have to do is, let me think. Let me see here. We need to take, so because I have to do 1, 0 star, 0, then 0, 1. I already have 0, 1, 0 over there. So all I'm going to do is I'm just going to go, because remember, this is R. And then all I need to do is connect it to S by taking the final state of the original here. I'm going to, now you got to imagine it's going through this way. And I'm taking an epsilon transition that takes me, so there's an epsilon transition that's happening from there all the way over here. And then that will take me to here. Does everybody see that? So all I'm doing is I'm concatenating the two. So now I have to label the start state. The start state was way over here. It's way over here. I'm just adding an arrow off the start state of 1, 0 star. And the final state would be way over here. This is the new final state. So when I build it up like this, I have bits and pieces I can use to combine them. Now, of course, when you're actually doing this, I'm reusing pieces. Like if you're actually like to generate this automatically, you'd have each piece, then you would like assemble it by using these so-called regular operators. But does everybody get the example here? So all I'm doing is I build up the pieces using the cases, and then all I do is I work. Oh, wait, actually, perfect. Perfect. I didn't realize I could see the start state so easily. Wonderful. In fact, let me move us a little bit over this way. Then I could get the whole thing there. Here's the whole thing. There we go. Perfect. So there's the whole picture. Bam. Here we go. So there we go. We got the whole epsilon-NFA when we're done the construction. Is everybody good with this? Are there any questions? I have to ask you because I'm going to make you do it on the assignment. Okay, I think we're good. Are we all good? Give me a thumbs up. Okay, perfect, perfect. Okay, good, good, good. Awesome. So what I'm going to do now is I'm going to transition over to the other part of Kleine's proof. Kleine's theorem. Okay, quite excited. I got so excited my little penguin fell down. So let me just move us back over this way. So I'm going to have to I want to prime you with a couple of pieces of information that are going to be kind of helpful for this proof. I want to give you some intuition behind this proof before we get in there. There's a lot, I like that comment. There's a lot of organic chemistry in this computer science. That's a wonderful comment. It does actually, it's kind of like that. I like that comment. That wins the day. Okay, so I want to warn you just in advance, this part of the proof is a little tricky. It's because of the way we use induction. Because every time we've done this up to this point, we've always done like induction on the length of the string typically, right? Well, I'm going to use induction in a somewhat different way. And this is, you have to be very careful with this. So I'm going to, I'm just going to give us some background for the proof so that the proof can flow a little easier. Because I know when I first learned this proof, I had a little hard time accepting it at first. Because like, okay, this doesn't, I don't know why we're talking about this. And I feel like I want to give you that kind of background to help a little bit with this. So to set up the second part of the proof, This is the proof. Let us define for a DFA-D, for a DFA-D, its states so that they are labeled 1, 2, all the way up to n, where n is the number of states. So I'm just going to make this assumption at this point forward. You can do this with any DFA. You can label all of the states differently, right? Just like when we built DFAs, we were allowed to relabel them. I'm going to relabel them to always be where the states are labeled 1 through n. I'm going to need that for let us define for DFA-D states so that they're labeled 1 through n, and the concept of a k-path. So I'm going to need this thing called a k-path. Now, if you're thinking of like a path that contains k edges, that's not what I'm referring to in this context. This is going to be something very specific. So I must warn you that at first it's going to seem a little bit alien of why I would do this. And then once you see the example, my hope is to reveal to you how k-paths connect regular expressions with the DFA. So here's the definition of a k-path. It's so very simple. It's a path. Now, when I say a path, I'm not referring to a simple path. You're allowed to have it so it can repeat on vertices or nodes, whatever you'd like to call them in this path. So I'm allowed to revisit the same ones over again. So you might know this as a walk. A path where every vertex, so I'll use the words vertex and state as synonyms very often. For every state contained in it has a label. Has a label at most k. At most k. Except the ends of the path. So what I'm saying is that if I give you a path from like state 1 to state 2, for example, I would say that state 1 is the start of the path, state 2 is the end of the path. So if I gave you a path, let's say length 3, and it went from 1 to 2 to 3, and I'm asking for a path from 1 to 3, the only way this path can go through state 2 is if it's a 2 path. So notice that this is actually telling me some bound on all of the ones in between. So I'm going to do an example with this one moment. And I must stress, I'm going to use a convention with you to save me a little bit of time writing things down. So I'm going to refer to the label of a path. So let me write this down. This is just a matter of simplifying things for myself when I'm writing this for you. Otherwise, I'll be writing a lot more than I need to. For simplicity, we will call the label of a path is simply the labels on the arcs or transitions that are in the path. So what I'm saying is this will correspond to the string that you feed the machine. So if I go from state 1 to state 3 and I use a string, so I require a string that causes the transitions to go from state 1, state 2 to state 3. The string that allows that to happen that would be what I'm referring to as the label for that path. So the path will take on transitions. So it'll go from one state to another to another. I'm going to refer to the symbols, which are the labels. These are corresponding to your input symbols that you process for each transition. I'm just saying, if you travel from one state to another, all of the symbols you use to transition to those states, that's the label of the path. Is that clear, everybody? So I'll do an example. Hopefully that'll explain this idea, but I want to give you something that actually motivate this so that you can see why exactly we care about this concept. So I'm going to draw a DFA. This is going to be a rather simple one. And so let's give me the start. I got states 1 and 2 here. And what's going to happen? Oh, I need to label this as a 1. So what I'm referring to as a label in a path is, say for example, I transition from 1 to 2, then to 2 again. One example of a path, a label for this path would be 1, 1, for example, if I were to just read it off. So I'm just telling you what the string is I use to get me from one state to another. Is that clear, everybody? I just want to use this because it makes things a little easier for me to write down in the proof. So if you wonder what a label of a path is, just think of the string you use that you give as input to your machine from a given state. So you just think of the extended transition function from a given state. Are we all good with that? Because I want to now do some examples with this k-path idea. So the big thing is that we can use k-paths to help us describe strings that are accepted by the DFA. So we're going to use this idea, and then I'm hoping that I can convince you that a very specific kind of k-path will actually correspond to the regular expression for the DFA. That's what I'm going to try to convince you of. So imagine I wanted to have all the zero paths from 1 to 2. So if I want to take the zero paths, so remember the zero paths, so if I plug in 0 for k up there, it says a path where every vertex or state contained in it has a label at most 0, except for the ends of the path. So when you look at this, if I'm considering from 1 to 2, I get 1 and 2 for free because those can be the ends of my path. But notice something. Can I take this self loop on 1? Can I repeat this several times? The answer is no, because now I have a path. Say if I take a self loop, say if I go 1 to 1 and then I go to 2, that would be a path 1, 1, 2 like this. So notice that this is not a 0 path, right? Because this is greater than 0. Now, the neat thing about this, so first, are we clear about that? Why this isn't a 0 path? However, if I go from 1 to 2 directly, that is a 0 path because the ends aren't counted. So the start and the finish are not counted as a part of this check to see if it's at most k. Are we all good with that? I know this is one of these little technical things, but I know it creeps into this proof a little bit if you aren't careful. Okay. So if I have all the 0 paths from 1 to 2, if you really think about it, I want to think about it like a regular expression. I want you to imagine, I want to know the strings that get me from state 1 to state 2. And because state 2 is a final state indeed, that these would be strings that get accepted. Can somebody describe to me a regular expression using a 0 path? So any of the 0 paths, which might I say, this is the only 0 path. Can somebody describe to me a regular expression that if I were to feed you a string from that regular expression, that it would accept on this DFA if it's a 0 path? I tell you, it's very simple. So don't overthink it. Just one, that's it. So if I just give the expression 1, that represents all possible 0 paths of strings that can get me from state 1 to state 2. In this example, this would be all possible zero paths that actually correspond to strings that get accepted by this DFA. So I'm hoping I can ease you into this, and then you can see the connection. So all the 1 paths from 1 to 2. So if I want all the 1 paths. Now, I want you to revisit what I just said before, where I can go. So first, to be clear, if we have a 1 path, you know that I can't revisit 2 several times, right? Because this label's too big. But it can be the end of a path, right? That's allowed. But I can take this loop several times, as many times as I like. So I want you in your head, just think about it. I can take this as many times as I like. Then I can go to state 2. So what is that as a regular expression? Can somebody tell me? Yes. Yeah. Perfect. That's exactly it. So notice I could use 0 star. So remember, 0 star, so I could take 0 as many times as I like. Then I could go to state 2, right? So this is the path from 1 to 2. It is a 1 path. Any 1 path can be described by this regular expression. Now this is where it gets a little trickier. So I'll for the sake of time, I'll just write it down for you. But I'll let you think about it. All the 2 paths from 1 to 2. So now think about it. I could take that loop at the beginning. So you know that, okay, the 0 star is definitely going to be there. I'm going to definitely, to get to state 2, I need to take that 1. So I know that. But notice that I can, because it's a 2 path, I can take 2 as many times as I like, right? So what I could do is I can take a 0 or a 1. I could take a 0 or 1, and I could do that as many times as I like, and I could stay in 2, right? So these are all the 2 paths from 1 to 2. Now, this is the neat part. What I just described to you, let me just write that 1 a little bit further to the left. There we go. There we go. So if you think about it, 0 star 1, 0 1 star. If you think about it, this looks a lot like all the strings that should get accepted by this DFA. Does everybody see it? Like I said, this k-path idea seems really alien, but when you think about it, but what is a 2 path? This is an n path. So if n is equal to 2, you get an n path. So if I consider all of the states in my DFA, and I start at, say for example, if the start state is 1, and I label for you the final state, say 2, like keep in mind there can be multiple final states. I would have to do this for each one of those. And I take them all and lump them all together into a bucket. I should be able to give you a regular expression. And that regular expression should correspond to the language of the DFA. Does everybody see that parallel going on here? So if I get an n path, and I take it from the start state to a final state, I should be able to get all the strings described by a regular expression that get me from that start state to that final state. So if I want to get it for the entire DFA, I do the same thing over all the final states. In this example, there's only one final state, so this in fact would be the regular expression I can use to describe this DFA. Well, the language of it, to be more precise. Are we all okay with this? So I just really wanted to give you this idea. Yes? Yes, please, please. Yes. So the order does matter. So for example, just let me give you an example. If I were to write 1 and then I gave you a bunch of zeros, like I have there, like if I flipped 0 star and 1, notice that the 0 star is actually representing this loop where I can go as many times as I like. The 1, however, is going this way. But I must stress that concatenation is not what we would call, and the other day I actually incorrectly stated, I wrote associative, it's actually commutative. So that means that you can't, in concatenation, you can't commute or permute, if you prefer that term. You can't swap two unless they're literally equivalent to one another. But you have to be careful and always look at what it says carefully. In this case, I can't swap these two, nor can I swap these two because they mean actually quite different things. But that's a really good question. But yeah, the order in which I do this, and you might ask, Dan, where the heck did you get this? And the answer is the proof I'm going to give you shows you exactly how to build this. So if you're wondering where this came from, I would not expect you to grab this and pull this out of nowhere. Unless like you got a little cozy with this. I only do it because I'm cozy with this. But once you see the connection, hopefully it'll click a little better. Does that sound great? Perfect. Yeah, no, so I think we got the general gist of the idea. So what I'm going to do is I'm going to use induction to build broader and broader k paths. And I'm going to start at k is equal to 0, start at a 0 path like I did. And what I'm going to do is I'm going to build broader and broader k paths until I get the k is equal to n. And I'm going to do this on all of the possible pathways that I can get from the start state to the final one, or any final one. Then all I do is I lump them all together into a one bucket. So that's going to be the general gist, and that's how we're going to get the language of the DFAD. So as soon as you see this connection between an n path from a start state to a final state and collecting them all up, then this is essentially the idea. So I'm going to walk us through this. So here's the theorem. If language L equals L of D for DFAD, then there is a regular expression R such that this is such that looked like it was kind of turning, it was kind of having its day, such that it sees Friday and it's like, oh man, I need to get out of here. I'm just joking. Okay, so let's do the proof here. So I'm going to give you the setup. I'm going to combine all the ideas I just described over here and what I just said and to write it a little bit more formally. So suppose language L equals L of D for DFA D, where it states are labeled 1, 2, all the way up to n. So these are going to be what my new labels for the states are going to be, 1 through n. Like I said, you can relabel any... Oh, no worries, no worries. So I'm going to relabel them like this. Now this is where, like I said, this is where I usually, like when I remember when I was first learning this is where I lost it a little bit. So I'm hoping this will help connect the pieces here. So let R subscript ij k, where the superscript is a k with parentheses around it, be the name of a regular expression, whose language contains the strings W so that W is the label. And remember, when I say this, I'm talking about all the transitions read along a path. Of a k path from state I to state j. From state j in D. So if you're wondering what I and j are, in my example I used 1 and 2. So I was 1, j was 2, and this is the name we're going to give it. It looks a little intimidating, but I assure you, once you get the idea of how this construction is going to work, it should hopefully kind of come together a little bit. So are we okay with this statement? So all I'm really saying is that this is going to be my name of my expression, and its language is going to contain all the strings such that they're going to be some label on a k path from state I to state j. Okay. Hopefully this setup helped a little bit, because this is honestly, like when I talk to students about this is usually the part that I lose some people. Well, I didn't, but I know when I was an undergrad, this is what got me. So let us perform induction on K to define. So I'm going to build this expression inductively to define Rij superscript K. K is equal to 0, 1, 2, all the way up to n. We will use this to prove the claim. So, dude, prove the claim. This is the claim. Man, it's Friday, man. My apologies. So we're just going to do induction on K. So remember K, this is the K from the K-path definition. So remember, the intuition you want to have is that we want to work our way up to when K is equal to n. And if we can identify the correct Rijk for each one of our paths from a start state to a final state, we can take those expressions and perform union operations along them. That's going to be the idea. So I'm going to describe how you build this using induction. So it's going to be kind of like when we did it the last day, except I'm going to have to be really careful because it's a little bit, it has a few little steps that are a little trickier. Okay. So let's do the induction. So here's the tricky part. Is this induction? But I assure you, if you were cozy enough with the previous one, once you got the idea of the K path, this isn't actually that bad really at all. So I'm going to start off with the basis. I'm going to assume K is equal to 0. So when K is equal to 0, all the states are labeled. So just remember, all the states are labeled from 1 or higher, right? So it means if I have a 0 path, we just make the same observation I said earlier. All the states are labeled 1 or greater. 1 or greater. So any 0 path contains no intermediate vertices or states, whatever you'd like to call them. So remember how I went right away from right to 1 to 2, but I couldn't take any of those self loops, right? I just went right from the start to the end of the path. That I didn't have anything in between. That's all I'm saying here. So when I say no intermediate vertices or states, that's all I'm saying. So we're going to go right from I to J by an arc or transition, whatever you'd like to call it. So now I want you to observe there's actually two possibilities here. There are two possibilities. Possibilities. I'll say two cases, just because I'm kind of running out of space here on the right. Two cases. There are two cases. So you might ask, Dan, what are these two cases? Well, you notice in my picture I had when I and j, like remember I had I and j, right? Like I could have it where I could take a self loop, but what would that be? That's when I is equal to j. Or I could be that I go from I to j, which j is a different state from mine. So there's going to be two cases. I is not equal to j, and when I is equal to j. So in each one of these cases, I'm going to describe to you an expression that we're going to describe using this fancy R notation that I have here. So when this happens, it's just simply going to be an arc from state I, from state I to state j. Then we consider D and find inputs. Find inputs. Or input symbols. Let's go input symbols. I like that a little bit more. Input symbols A, where there is a transition, where there is a transition from I to j on A. So I'm just going to look for transitions. And depending on how many symbols I have, that's going to change one of our three possibilities here. So when I have no symbol, so there is no such A, when there's no symbol, then I'm going to write the expression Rij superscript 0 is going to be the empty language. Why? Because if there's no way I could go from I to j on that transition, then there surely is just nothing I can. There's no way I can have a language between one state to the other. You got to look at it as very much like I'm trying to get from a start state to a final state. But you got to remember, I and j don't necessarily have to be the start state and the final state. So it's going to be like I'm intermediately building, like I said, broader and broader strings that are going to be expressed through regular expressions. So I have one symbol. So this is if I just have one symbol and say that's A, just A. Then I can write Rij 0, and I could just use the expression for the symbol A. So far, are we doing okay? So all I'm going to do is I'm just describing, like when I did my example on the board earlier, when I wanted to go on the 0 path from state 1 to state 2, this is exactly that case. So here then I can also have it where I have multiple symbols. And suppose that they're called A1, A2, all the way up to AK. Then R superscript 0, Ij, is equal to the regular expression that consists of those symbols, like so. So just to make it a little easier, if you really just need to see this as a picture, what I'm saying is if you have two states, say it's a state I, and say you have a transition on J, and say their symbols A, B, and C, like this, what I'm saying is that you could rewrite this as the following expression. So as I just take the symbols, then I just perform the union on them. So that's all I'm saying, is that if you have one symbol, you just have just one sitting on its own. If there's none, there's no interesting strings there, right? Because I can't transition from I to J. So are we okay with these three cases here? So if we're okay with that, I'm going to do I is equal to J. Now, the great thing about this case is you can imagine it like you're just going from one state back to itself. And naturally, this is, then I could say then the 0 path, and the 0 path contains only some vertex or state, whatever you'd like to call it, vertex or state I. Meaning, if there is a transition, on symbols A, it will be a self loop. Now, you remember when I was kind of describing the language to you? I kind of said, okay, well, I could take the self loop, or I can go and take an arc from one state to the other state. I have like an option. It looks like an option. So in the world of regular expressions, when we had an option, what did we usually use? We used the symbol to do that. It started with an E. Can somebody tell me for me? What is it? Not epsilon closure. No. It's very close though. Very close. It starts with an E. What symbol is it? So we have a name for this as an expression. Then, epsilon. So epsilon operates like an option. So we could either take the self loop, or we may not take the self loop. That's good. What this is going to function as. Then we include expression. Then we include expression epsilon with each of the above cases. So what I mean by that is that you would just simply take, so what I would say is that, like what I'm saying is you just add epsilon here if you have no input symbol. Now it's worth noting that if you have the empty set and epsilon like this, you got to think back to what this means as a language. So if I have the empty set or empty language, union a set containing epsilon, this is of course just epsilon itself. Here I would just have epsilon like this, and I would just tag epsilon like this. So that's what would happen if I have I is equal to j. So are we okay with case number 2 here? So this is what you would do with any zero path. This lists out all the possibilities of what could happen. Now, just for the purposes of time, because I think we're out of time right now, I'll come back to this next time and we'll do the induction case. Just because I also want to make sure I give you back some time that I've been taking the last few lectures. So when we come back, we'll do the induction part of this proof, and then we'll do an example, and we'll see where we go from there. Okay? So that being said, hope you have a wonderful weekend. I'll see you later.